There is something very sad and, well, very interesting, I guess, about North American math textbooks. More often than not, they tend to start off with a chapter or at least a couple sections that are, oh, what is the point of math? Why do we do math? How does math relate to everyday life? Well, there are many ways in which math relates to everyday life. For example, the house you live in was most likely built by an architect and of course a building company. And they have to design this with considerations as to, oh, load-bearing elements and so on. And say, oh, thermal effect when it cools down in winter. What happens? Well, we know that different materials shrink differently. So we need to contemplate what that might do to the material of the house. Of course, in math, it's a great deal more tedious than the science version. But fortunately, we at least have some example problems, which are a little bit less boring, hopefully. Alright, so first we need to start off with stuff like, oh, solving problems, communicating our solutions, or communicating information in general, and connecting between real life and math expressions. So technically speaking, calling this chapter 1.1 is a little bit off the mark, because most textbooks use several different sections for this. So let's just say it's up to 1.3. Alright, in terms of vocabulary and concepts, first you need to know what you're looking at in the problem, which is why, well, understanding is the first main concept you need to deal with. Then you need to plan what to do, and then you need to actually do it, so solve the problem. And then you need to check the problem. This is a little bit different from the science version. The science version is start. So initiation and planning, they call it. And then do it. And then you analyze. And then you present or communicate it. Because there's a saying in science called publish or perish. So either you publish your results or they're completely useless. Now in math, on the other hand, since we're not exactly publishing anything for now, we are first, look at the problem, figure out what to do, so plan, start. And the planning is, well, planning. And then we actually do the problem, and we look back to analyze it to see if it makes sense. And of course, we omit the presentation part. So, example 1, patterns and sequences. Well, we should know that patterns can solve problems. For example, if we've ever done any pattern problems in lower grades, which I'm sure everyone has, because it's in literally every math textbook ever, pretty much. So here we need to find the next three terms. What happens? 3, 7, okay, that's plus 4, and then plus 4, and plus 4 again. So the next three terms would be, well, plus 4, which means 19. And then what? 23, 27. And now for this one, find the next three terms. Oh, 8 to 4, well, that looks like 1/2. But wait a second, it's negative 8 to 4. So times negative 1/2 times negative 1/2. This seems to be the pattern for 4 to negative 2. Yeah, okay, that works. And then negative 2 times negative 1/2 is equal to 1. Okay. So this is the pattern we are looking for. Therefore, the next few terms would be these. Now here we have 10, 10, 20, 30, 50, 80. So here we have plus 0. Plus 10, and then plus 10, plus 20, plus 30. This looks like you're adding the number before this. So here, 20 to 30, you add 10. to 20 and you get 30. 20 plus 30 equals 50. 30 plus 50 equals 80. Okay, this is a Fibonacci sequence. So the next term would be 50 plus 80 is equal to 130. 80 plus 130 is equal to 210. 130 plus 210 is, well, 340. And that's it for that example. Now here we had to not only solve a problem, we also had to communicate it, and we had to connect it. Well, we had to make the connection that this set of differences was related to the set of numbers. And what about communicating? Wait a second. We've been doing communicating this whole time. All these symbols. See this? This letter here? That's a form of communication. And of course, me talking at you is a form of communication. Here we will connect between these symbols and numbers. So we're looking for how many circles will be in the 10th stack. So we have 1, 3, and here we have 6, then we have 10, so it's plus 2, plus 3, plus 4, and okay, so for the second stack we had a plus 2, for the first stack we had a 0 plus 1. What does that mean for the 10th stack? That means for the 10th stack it would be 1 plus 2 plus 3 plus dot 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 plus 10. Right? Wait a second. How many are we actually adding for the 10th stack? Okay, for the third stack we added 3. For the fourth stack we added 4. Okay, good. We need to check regularly and at various steps in our problem whether or not our thinking makes sense. Alright, so here we have 10 numbers, each corresponding to one item, and this is equal to 11 times what? Well, wait a second. 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. That way we pair them up, and then we get 11 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means 5. And this is equal to 55. Now, I'm sure we've seen some cases where somebody just wrote this. This is not actually necessarily bad. Like, it's not something most teachers will reject, but it is not good form. Now, we notice something else. We lined up our equal signs here. Why is this the case? Well, can you imagine solving a problem where we end up with this? This is a little awkward, right? To trace the progress of a problem down a page, especially if you have several columns. Yeah, it is a bit awkward. All right. So why do we use the current numeral system that we have now? That's basically combinatoric position based. I'm pretty sure that is not the exact scientific term for our current numeral system. However, the point remains that you combine a bunch of symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, and you position them to indicate a particular amount. Now this is of course very different from, say, 1, 2, 3, 4, and 5, 6, and so on, Roman numerals. Now, why do we use our current position-based system with 10 symbols instead? It's because, quite simply, there are many numbers where if you use numerals or any Roman numerals or any other symbol-based system, you end up with a ridiculously huge number of symbols. That is why a position-based numeral system ends up being better and is what we use now. Now you might be thinking, hey, if a position-based numeral system is better, then why don't we use, say, the Chinese system where they literally say 1,400, and when they write those out, they actually include the 1,000 and 100 symbols. It's because, well, quite simply, this is much easier to code for. And also, what about point something? This is much easier to code for in terms of the number of symbols that you need to code into a computer. And for various other reasons. Namely, there's less writing, and when you line the numbers up, you can line them up a little bit easier, especially if you have lined them right justified. Now you might be thinking, hey, isn't traditional Chinese text vertical and right justified? There's a little problem. Those things begin at the top of a page. So it's top justified. On the other hand, if they were bottom justified with the units at the bottom, sure, fine. They would have been lined up nicely. And you may have known that an abacus, i.e. the ancient Chinese calculator, the ancient East Asian calculator in general, more like, that system is basically position-based. So the only difference in terms of that versus that sort of position-based system versus this is that really each of those is actually a tally system. There's a 5's dial up top and the 1's on the bottom. Which means that basically what you're doing is this. This is in the 1,000th position, and this is in, say, the 100th position, and so on. Now these are all supposed to have columns, and these are represented by the little beads at the top of the abacus. So there's a little problem with this too. Why? Because you'd have to be careful to make sure that you end up with the 1's on the right side, and also the number of digits that you can possibly calculate on that thing are quite limited, especially if you have to suddenly venture into decimal territory or fractions. Now, connecting. Now, graphs and diagrams, I mean, I'm sure you've all seen tallies. Tallying is, in a sense, a type of graphing, but it is a representation of real-life problems with a mathematical model. In this case, a mathematical representation. Now, graphs and diagrams in general are ways to connect real problems and math models. Actually, above those problems we solved, they could have represented some actual phenomenon that you happen to observe in nature, and say the particular whorl pattern of a leaf. You might be thinking, hey, why are these leaves growing out at a particular angle? What's so interesting about this? And then you might go back and calculate and find that that is the optimal angle for catching as much of the sunlight passing through as possible. Now, when you do math, there are many problems actually, that do have exact answers. However, there are also some problems sometimes that you might have to deal with that don't have any particular answer. It's an approximation at best. These are called Fermi problems. They're named after Enrico Fermi, who was born in the early 1900s and lived until the 1950s. So Enrico Fermi liked to pose these problems where it was like, hey guys, how many hockey pucks, or footballs rather, do you think might fit in this stadium? Why footballs? Well, quite honestly, it was because this guy worked on the Manhattan Project in the United States. So footballs instead of hockey pucks as a Canadian example. So guys, how many footballs might fit in this stadium? And then people would have to make some assumptions. Oh, okay, the football has to be about this size. They have to fit together in a particular pattern, because as we should know, if you fit a bunch of footballs like this, that's not as effective as if you stagger them. So, like this instead. Of course, footballs do not look nearly this cigar-shaped. It's just artistic skills are a little bit hard to manipulate on this device. Now, you can do some Fermi problems as well. This takes some estimation and some assumptions as to how the pucks or balls or whatever are packed. So you could use, say, hockey pucks versus your room, or hockey pucks versus your bathroom, because that's a smaller space, a little bit easier to estimate. And then you can have fun doing some Fermi problems. Well, of course, I'm personally not very interested in Fermi problems. I'm more interested in just problem solving in general, with problems that do have certain answers. Alright, so if you wanted to go do some Fermi problems, now would be a good time before we proceed to the other half of Chapter 1, i.e. the what is math, how do we use it, and what it's about in general chapter.